Yeah, the audio is quite a bit better if you use GoToMeeting than it is on our phones, but that's okay. We can make do. Yeah. Apologize for not having you on the calendar. For some reason, when your mom scheduled that session today, it didn't show up. God, you know, I'm wondering is if it showed up next week. Let me just look quickly next week. No, didn't show up next week either. Interesting. I wonder what happened to that. Yeah, I saw she made a payment, so I saw the payment, but I wasn't sure what it was for. So, all right, let's have a look at some of these problems here. You want to start at the beginning? Do you need to start at the beginning, or do you want to start?
Let me just like review two from each set.
Sure. Let's look at one. Y equals 3 to the x plus 1. Okay. Best way to do this is to use the parent function. What's the parent function? Y equals 3 to the x. In other words, here's the parent function. Y equals 3 to the x. Any exponential function always looks like this, right? Whether it's 3 to the x or 2 to the x or e to the x, you can't tell the difference from looking at just the graph. And all of them go through the same point, which is 0, 1. Notice that if I let x be 0, y is always 1. So even if I were to graph y equals 17 to the x, it would look a lot like this. You wouldn't be able to tell the difference from, unless I label the grid.
Hey, Jay?
Yeah. I got you on the speaker now. Let's hang the phone up.
I'll shut the phone off, then we'll go to the speaker then.
There you go. That works good. Can you hear me?
How's it working?
Really good.
Hello?
Can you hear me? I can hear you.
All right, yeah, I can hear you too.
Okay. Let me open this. Let me make sure that I got everything right here. Yeah, I do. Okay. So what I've drawn is y equals 3 to the x. Okay. What's the difference between y equals 3 to the x plus 1 or y equals 3 to the x?
Would it just be moved up? Would the
yes,
y
exactly. Be moved up? Now, y equals 3 to the x has asymptote where?
Would it just be at 2? No, a 1?
No, it actually is at y equals 0. Always remember your asymptotes are equations of a line. Okay, y equals 0 is the x-axis. And all of these exponential functions, if you go far enough to the left, it gets very, very close to the x-axis. It keeps getting closer and closer and closer without ever reaching it. You with me?
Yep.
So if I take that function that has a horizontal asymptote at y equals 0 and I move it up 1, what's the new horizontal asymptote?
Would it be y equals 1?
Good. And what's the new, I'll do it in red. What's the new y-intercept? Excuse me, just 1 second, if you would.
Okay.
Hello? Hi, Zach. Yeah, sorry. Listen, I'm in a session, but I just wanted to say one thing to you about that problem. I figured out what I was doing wrong. you cannot do calculus on degrees. Whenever you're doing a calculus problem involving trig functions, they must be in radians. So take that 30 degrees and make it pi over 6, and then try to do the problem. And I think you'll get a more reasonable answer. Okay? And if you were to look in your book, you'd see that they're doing them all in radians, even though they give it to you in degrees. I was just trying to fool you. Okay, so I got to run. Talk to you Monday. Okay, bye-bye. Sorry about that, Jake.
That's fine.
I had a session and we had a calculus problem that I couldn't figure out how to do. I realized how to do it on my way home. So the y-intercept is what now?
It would be y equals 2.
Well, that's again the equation of a line. The y-intercept is a point.
So yeah, I mean 0, 2, sorry.
0, 2 are the coordinates of that y-intercept, and that's all they need. Okay? Now, let's take the next one. 2 to the x minus 2 minus 3. Tell me what two things are happening to the, what's the parent function, first of all?
It would be y to the 2x.
It'd be 2 to the x. Y equal 2 to the x. Remember, all of these exponential equations are exponential because the variable is always in the exponent. That's what makes them different than algebraic equations. Okay? Now, what does this have happening to it? I can draw the parent function. Again, is going to look just like that. And it's going to go through 0, 1, despite the fact that it's a 2 instead of a 3. If I had a grid on here, they wouldn't look exactly the same, but the shape of them is almost always the same. Very similar. You can't really tell the difference by looking at the graph, that it's 2 to the x instead of 3 to the x, especially since they both go through this same point. They both have that same y-intercept. Okay, what's going on? I know you know that that's a shift down of 3. What's the consequences of that?
Would it be a shift right too?
Yes. Okay, so what I do is I take that point, I move it to the right by 2 units, and I move it down by 3 units. So it goes right there. That point does, and that point is now 2, minus 2. And the curve, same shape, but has a different horizontal asymptote. What's the horizontal, and there is no vertical asymptote on these, incidentally. In other words, x can go all the way to infinity, but y has a bottom on it. So there is a horizontal asymptote. What's the equation of this dotted horizontal asymptote?
Would it be y equals -2?
Yeah. And we got to figure out that point right there. They want the y-intercept. What's true about the y-intercept? What's true about x when you're on the y-intercept?
That x equals 0.
Okay, so take this equation, plug in x of 0, and what do you get?
You get -2 to the...
Not -2.
I'm just working it out, sorry.
You get 2 to the -2.
And that would make it -1/4?
No, positive 1/4. Negative exponents do not mean negative numbers. It's a mistake that people make a lot. All they mean is reciprocal. In other words, when I say 2 to the -2, that's a positive number. It's 1 over 2 to the positive 2, or 1/4. Okay? So when I substitute 0 for x, I get 1/4 minus 3, which is minus 2 3/4. So the coordinates of that y-intercept are 0, comma, minus 2 3/4. Okay? You good on that one?
Yeah.
And you would do the same for all of these. After you've made the shift or the reflection or whatever is called for, then to figure out the new y-intercept, which isn't going to be obvious at all, you just plug in 0 for x and see what you get. In other words, the y-intercept on this one is minus 1 plus 2. So the y-intercept is 1 on number 3. Number 4, the y-intercept is 0, because 4 to the minus 0 power is 1. Anything to the 0 power is 1. 1 minus 1 is 0. And let's talk about one other thing with 3 and 4. What's the negative sign on 3 do? Vertical reflection or horizontal reflection?
Horizontal?
No. Anytime you're outside of the function, everything is vertical. In other words, if we go back to problem number 2, see that x minus 2? That's inside the function. That means it's horizontal. Outside the function is the minus 3. That means it's vertical. Okay? This negative sign is outside of the parent function, e to the x. So that means it's vertical. That's a flip over the x-axis. Okay? Number 4, the negative sign is inside the function. That means it's a horizontal reflection. It's a flip over the y-axis. And you always do your reflections first, not after you've done your shifts.
Okay.
All right, let's be done with that part. You said you want to do 2 from each section, maybe?
Yeah.
Okay. So on the next one, they want x-intercepts, not y-intercepts. And let's talk about the parent function on the first one. Hold on, I want to draw my parent functions in black. Parent function is what?
Log x.
Log base 3x.
Okay.
Okay. Now, log functions are a lot like exponential functions, as they should be, because they're the inverse. They all look like this, regardless of their base. And they all go through that same point, which is 1, 0 instead of 0, 1. You with me?
Yeah.
This also does not have a horizontal asymptote. The fact that it looks really, really flat doesn't mean anything. In other words, x can go to infinity and y goes to infinity. Okay? So the function we're dealing with differs how?
Isn't it basically just an inverse of a normal?
No, in other words, we're looking at number 5. In other words, our function is y equal log base 3 of x minus 1. So all we have to do is figure out how that's different from our parent function.
Would it change the x-intercept to...
What is it called? Is it a horizontal, a vertical, a stretch, a shrink, a shift?
Would it shift it right 1?
Yes, it's a horizontal shift because it's inside the function. It's not outside. If that was a minus 1 out there, that'd be a vertical shift. Okay? In other words, outside the function is always vertical stuff. Inside the function is always horizontal stuff. Well, to shift this to the right of 1, this does incidentally have a vertical asymptote. The original one does. Goes right through there. What's the equation of that line?
X equals 0.
Correct. Now, when I shift everything to the right, it shifts that vertical asymptote 1 unit to the right also. So that now, and notice they didn't ask for a y-intercept because we don't have one. But we do have an x-intercept. What's the new x-intercept?
2, 0.
Okay. Next problem. Y equals minus log x. Well,
Would this be vertical reflection?
Yep. There's the log x, and the minus sign being outside of the function means it's a vertical reflection. So basically, it's that. And that point's the same. It's still 1, 0. So the x-intercept is at 1, 0. In other words, the vertical reflection doesn't do anything to points that are on the x-axis. Let's look at 7. Let's at least look at one of these where the negative sign is inside the function. Y equals log base 2 of negative x plus 1.
It would be a horizontal reflection, correct?
Yeah. Well, let's see. And we're going to do our reflection first. So there's what the parent function looks like. Horizontal reflection would look something like that. And this point right here is what? At the moment, in other words, after just the horizontal reflection, what is that point?
Negative 1, 0.
And after we move it up 1?
Negative 1, 1.
Well, I know this point moves up to there, which is negative 1, 1. The question is what is the new intercept? Because it's not the same as the old intercept. Oh, no, it isn't. How do we figure it out? What's the y-intercept equal to?
Just said
what is
0.
What is the y value when you're talking the x-intercept? In other words, if I want to find that point right there, I'm going to set y equal to 0. And if I set y equal to 0, then I have negative 1 equals the log base 2 of x. And if I'm trying to solve that for x, then I'm going to say 2 to the negative 1 power equals x, right?
So 1/2.
Correct. So the coordinate of the x-intercepts is minus 1. Ooh, it's not minus 1/2. I see a big problem here. Problem is you cannot take the log of any number and get a negative number. That's impossible. So what did I do wrong here? We've got that. We're going to set y. Oh, there's no y-intercept. Oh, we're trying to solve for the x-intercept. So we're going to set y equal to 0, which is what happens when you're on the x-intercept. And then I have this problem. And when I bring the 1 to the other side, I get that, which is impossible. I'm trying to think for a second. No, it's not. You can take the log of a number and get a negative number. Excuse me. Whenever you take the log of numbers between 0 and 1, or for that matter, between 0 and minus 1, you get negative numbers. In other words, if you look at this original black line, well, you can see that I can take the log of a number between 0 and 1 and get a negative y. So there's nothing wrong here. Question is, how do I solve that? Oh, I see what the problem was. It's 2 to the minus 1 equals negative x, which means x does equal minus 1/2. In other words, 2 to the minus 1 is 1/2, but I need to take the negative sign that was on the x, move it over, so there is my x-intercept at negative 1/2. Okay. It is a useful thing to remember, though, that when you take logs of numbers greater than 1, you get positive answers. When you take logs of numbers between 0 and 1, you get negative answers.
Okay.
All right. The only difference on 8 is you're using natural log. You're familiar with natural log? That's just log base e.
Yeah.
Okay. And what's the x plus 2 doing?
It's words of I know how it's
Horizontal or vertical shift?
It's shifting it left.
Okay, that's horizontal. Left right is horizontal, up down is vertical. Okay?
Yep.
All right, let's look at number 9. Log base 2 of 1/16. Well, the way you evaluate these is the easiest way to look at it is, well, let's let it make it equal to x, and then we'll solve for x, okay? Same thing, right?
Mm-hmm.
It's important to put the x in there because now I want you to take this equation and turn it into an exponential equation. What's the exponential equivalent?
2 to the x power equals 1/16.
What's x going to be?
-4.
You got
-5.
No, -4 is right. In other words, 2 to the 4th power is 16.
Mm-hmm.
Okay. Yeah, that's really the secret here is add the variable. In other words, without the variable, I don't know how to turn that into an equation that's an exponential equation. But once I put the variable in there, now write this exponentially.
10 to the x power equals 1,000.
What's x?
3. X equals 3.
Okay. Next one, log base 7 of 1. This one I don't need to add the x. Why?
Would it just be 0?
What's the log of 1 always?
0.
Notice that if I had added the x, I would have been looking at 7 to the x equals 1. X has to be 0. But the log base anything of 1 is always 0. Okay, let's look at 12. That looks kind of interesting. Natural log of e to the 5? Is that what that is? Not an s, is it? No, it's got to be a 5. What's natural log of e equal to? Here, let's figure it out. We got the log base e of e. We'll let it be equal to x. So now we got e to the x equals e. What is x?
1.
Yeah. Which means that whenever you take the log of a number with the same base, it's always 1.
Mm-hmm.
So I can go through here and make each of these logs of e's 1, and we know that that 5 can come down in front, so I can rewrite this thing as 5 natural log of e plus 2 natural log of e. 5 times 1 plus 2 times 1. Okay, good with that one?
Yeah.
Okay, now we'll do the calculator ones. Getting the answer isn't as important here as going through the method of solution, but you might want to have your calculator handy. If you don't have it, you might want to get it, especially if you need answers on these.
I don't have a calculator on me.
You got it at school. Okay. Well, first of all, let's expand it. Log of the square root of 4x over 3. Well, let's write that differently using exponent instead of a radical sign.
Would we put 1/2 in front of the log?
No, it's like that. That's the same thing.
Can't we put 1/2 in front of the log too, though?
Yeah, I'm sorry. You were 2 steps ahead of me. This is the first step, is to rewrite it exponentially. Now you can bring the exponent down so that it's 1/2, and I get rid of the half here. Now, what about all the stuff inside the parentheses?
Would it be 1/2 log 4x plus, minus 1/2 log 3?
Yeah, exactly. And you could even expand it a little further. I'm not sure if there's any point to it. Write it as the sum or difference of simpler logs. Well, there's one more step you could actually take here to expand it. Notice that that's a product, right?
So could you just add 1/2 log plus 1/2?
Here, let me show you. It's 1/2 log of 4 plus 1/2 log of x minus 1/2 log of 3. And that does make it, it's the sum now of 3 different logs instead of just 2. So I would say, yeah, for this question, you'd want to go all the way here. Okay. Number 14 is going in the other direction, right? Wow. Does this look a little familiar?
Yeah.
Almost the exact same thing, isn't it?
Not quite, but okay. So let's put it back together.
So would it be log? Sorry, I'm just putting it through my head.
Well, the best way to put it back together is to take that coefficient and make it an exponent. So the very first thing you might want to do is this. You with me?
Yeah.
Do it for all places. In other words, that's the log of 3 squared. Okay. Now, the log of 4 to the 1/2 is log of 2 minus log of x minus log of 9. With me? Now, what's the single log function that they're looking for?
So it'd be log 2 over 9x.
You got it. Perfect. Okay. Should we try one more of those? Let's do 15. Simplify. The log of x plus the log of x plus 2 minus the log of x squared minus 4. Okay? So compress this.
So would it be log 2x, no. Log x squared.
Unmultiplied together for the moment.
Okay. Log, yeah.
And I'll show you why. What happens?
Over x squared minus 4.
Which is the difference of perfect squares. How does it factor?
Uh-huh.
How does it factor?
X plus 2, x minus 2.
Now notice that the x plus 2's cancel. That's why I wanted you to leave it unmultiplied. And almost always you want to leave it unmultiplied. Usually when you're looking at factors, that's a better answer than if you multiply it out. Okay?
True.
So what I'm left with is the log of x over x minus 2. Any restrictions?
No.
Well, x can't be 0. You cannot take the log of 0. You can take the log of positive numbers only. So x can never be 0. That's one restriction.
Uh-huh.
What else can x not be if you can't ever take the log of 0?
Can't be negative numbers either, so...
No, it can't be plus or minus 2 from this one over here. In other words, this third log statement, if x were plus or minus 2, I'd be taking the log of 0.
Which is impossible.
Right. So x can't be 0. In other words, all your domain restrictions come from the original function, not the final function. Notice that in the final function, x can't be 2, x can't be 0, but there's no restriction apparently in there where x couldn't be minus 2. I would still have a positive number if x were minus 2. I would have minus 2 over minus 4. I'd be taking the log of 1/2. So based on this, that domain restriction isn't there. But this is very important with logs because it's not obvious at all that you would do it this way. In other words, it's a little bit like a hole. You know what I mean when I say a hole?
Yeah.
Okay, it's not a vertical asymptote, but the hole doesn't, that domain restriction doesn't go away. Can I ask you to give me 2 minutes? I'm going to put my pizza in the oven so that it's done right when we're done.
All right, that's fine. No worries.
I'll be back in probably 60 seconds.
That's fine. Don't worry.
Jake? Jake?
Yeah, sorry.
Okay, I'm sorry, but my pizza's in the oven, so that's good. All right. Yeah, I didn't eat earlier because I didn't know I had this session. So 15 kind of illustrated something that even though they didn't ask about it, what the domain of the final single log was, it's affected. And all of these manipulations where you compress and expand, they're not identical. In other words, domains can be different. And you always have to use the domain of the original function. All right, let's see. 16. If log of 2 is 8 and log of 9 is b, if log of 2 is a and log of 9 is b, what's the log of 6?
Would it be A 1/3 B?
Rewrite each in terms of only a or b. Well, let's start with the log of 6. You might be right. I just got to think about it for a moment. That's the same as the log of 2 plus the log of 3, right? With me?
Would it just be A plus 1/3 B?
Well, hold on. Let's keep going here. So that's a true statement, right? The log of 6 is the log of 2 times 3.
Yeah.
Okay, and that separates out into the log of 2 plus the log of 3. Well, the log of 2 is a plus that is if the log of 9 is b, then this is 1/2 the log of 9. You see that? In other words, the log of 9 could be rewritten as the log of 3 squared, right?
Uh-huh.
So the log of 3 squared can be rewritten as the log of 3. So if the log of 9 is b, b is equal to 2 times the log of 3. Therefore, the log of 3 is equal to b divided by 2.
Mm-hmm.
And that's the answer, a plus 1/2 b. Okay, they could have made it a little, they could have given you an easy one to start with, where this would have been log of 3 equals b, and then the answer would have been a plus b. They gave you a fairly difficult one to start with, so let's do another one. What's the log of 72? Do it the way I did that one. In other words, separate this into some factors that have something to do with 2 and 9. What are factors of 72? Is 9 a factor?
Yeah, 9 and 8.
Okay, so it's the log of 9 plus the log of 8, right?
And you could break this down further.
Well, don't need to break the log of 9 down. That's b.
Would that just be 2b? Oh, no.
No, it's just b. Log of 8 is what needs changing.
Would that just be 4b? Or
No, it's the log of 2 cubed, right? Isn't that what 8 is? It's 2 cubed?
so would it be 3a?
Yes. In other words, that 3 comes down. The log of 2 is a, so you have b plus 3a.
That makes sense, yeah.
All right. So, in other words, a lot of these you're going to have to use powers. We had to use powers on 16. We had to use it on 17. Let's look at the log of 4.5. Well, how can I relate the number 4.5 to 9 and 2? Is that not the same?
So it'd be B over A?
Exactly. B over, well, no, hold on. You're jumping steps, and that's what's getting you in trouble. First of all, expand that. What's that equal to?
Log 9 minus 2.
Don't tell me my computer is frozen. Huh. Yeah, it's the log of 9 minus the log of 2, so it's B minus A. I got to close this out and reopen it. You see where it's B minus A?
Yeah.
What the heck's going on here? Okay. What is happening here? Never had this happen before. I gotta push draw. Wow. Sorry. Okay, so I think that solved the problem. Not solve the problem. Heck. I need to push that squiggly mark. Yeah. Some of these programs are ridiculously unfriendly, user non-friendly. So let's see. If we look at, you're kidding me. Well, I guess I got to push that every time. So we. Hold on, I got to figure out what to do here. Do not have another drawing program, I don't think. Let me see if this one works. Wow. No. Doesn't work either. Try reopening this one more time. Hit the draw, hit the squiggly thing. It's not picking up my writing, it's picking up my mouse. I'm probably going to have to unplug this and plug it back. Let me try this real quick. Yep, that's all it took. Okay, so where are we at here? We're at the log of 3 x plus the log base 3 of x plus 8 equals 2. Okay, the way you solve log equations is if you try to get a single log equation.
So do you want to condense it?
So what do I have?
You'd have log base 3x times log x plus 8.
No, it's just a single log. There's not a second log function in there. In other words, when you compress it, you take the 2 logs and you turn them into 1. In other words, remember what the rule is. The log of A times B is equal to the log of A plus the log of B. So if I'm going the other direction, I start with 2 logs and I end up with 1. And that's what we're trying to do here, is And you'll see why. So this is correct. Now what can I say? Now turn it into exponential.
Would you want to compress x times x plus 8 or no?
Not yet. Well, I guess you could. It's not going to, we'll eventually do that, but turn it into exponential first.
So it'd be 3 squared equals x squared plus 8x.
Yeah, now we'll do that. This is one case where you do want to multiply it together. So now it's going to be a quadratic. Factor that.
You'll get 9. Hold on. Yeah, positive 9 and negative 1.
Okay. So your answers are x equal minus 9 and x equal 1. Now, here's the thing about log equations. They almost always produce an extraneous answer. An answer that's no good because it violates the domain. Do either of these violate the domain?
Negative 9.
Yes, you cannot take logs of 0 or negative numbers. The 1 is fine, but the negative 9, so that's not a solution. The only solution is 1. Here's the kicker. You've got to go into that equation to test your domains. You can't use this equation. Notice that negative 9 doesn't violate anything. If I plug in negative 9 here and negative 9 there, I've got negative 9 times negative 1, which is a positive. So if I'm testing using the compressed equation, I'm not violating the domains. And that's why that first row you see is not identical to this second row. They're not identical at all. There are certain answers for x that violate the original, but don't violate the compressed version. And as odd as that sounds, that's the truth. Absolutely. You always have to go back to the original, which means these two things are not exactly the same. They're the same enough for our purposes as long as we know we're going to check our domains with the original. All right, let's look at the next one. Natural log of 4 minus natural log of x equal 1. Do it the same way.
You'd want to compress it first, so it would be natural log of 4 over x equals 1.
Now convert it to exponential.
E to the first power equals 4x.
4 over x. Right? You said 4x. It's 4 divided by x?
Mm-hmm.
Okay. What's x equal
to? Would you want to just multiply with the reciprocal, or?
Well, multiply both sides by x and then divide both sides by e. Whenever you're looking at something like that, if e equals 4 divided by x, then x equals 4 divided by e. In other words, I'm doing two steps. I'm multiplying both sides by x, and then I'm dividing both sides by e. There's your answer. Does that violate any restrictions, any domain restrictions?
No.
No. 4 over e is a positive number. And I'm always checking there. I'm not checking that one for domain violation. We do another one of these. Let's see. We got about 10 minutes. You want to do one of these half-life problems? Let's do a half-life problem. Just because these are not that obvious how to do. you tell me, it seems to me that our last session, this is the only one they gave you.
Yeah, that's the only one we're using.
Okay. That's not the correct one to use, incidentally. The correct one to use is this one, because it's continuous. Whenever you have continuous growth or decay, this is the correct one to use. And radioactive stuff is always continuous. You can get a bank account that is compounded once a year, but you can't get a radioactive substance that decays just once a year. So, all right, that's fine. I don't have any problem with them using this formula. It's an approximation. So, remember how we did these? Monday or Tuesday, I don't remember which. The half-life is 12 years. So what can I fill in here?
Y equals 1.3, A equals 5.
No. Half-life means that the original amount becomes half. So Y is A divided by 2. It's also why I had a little difficulty in solving this last time, because I've never had it before. In other words, when you use the correct y equal a e to the RT.
Well, isn't 1.3 already when it's decayed though? So why would it be?
Well, let's go through the solution of this. The a's cancel, right? Oh, excuse me, and I know what t is. They told us the half-life is 24 or 12 years. So t is 12. Okay? In other words, no matter what the original amount was, it turns into half of what it was in 12 years. And now the a's cancel. So I get 1/2 is equal to 1 plus r to the 12th power. That's only got one variable in it. I can solve for r. And again, how do I solve for r?
You 12th root it and then subtract 1.
Okay. So it's 1/2 to the 1/12th power. That's the 12th root of 1/2 minus 1. That's r. Okay? And you don't get numbers like this if you use the right formula. That's why it's a little strange doing it this way for me. In the other formula, the r is in the exponent, so it's actually easier to solve for. This particular one, where the r is down here, is actually a little harder to solve for because we're using an easier formula. It's a little strange. So now, to answer their question, determine how long it will take 5 milligrams of a substance to decay to 1.3 milligrams. Well, we know everything about it now. In other words, if I go back to the general formula, I know what R is. Okay, I'm going to erase everything but R. And let's start filling in. They want to know, they're asking about how long. So we got to solve for T. Okay, so the original amount is 5. The final amount is 1.3. We know what R is. R is this god-awful thing. Yeah, the ones cancel. To the t power. Notice there's only one variable there. How do I solve that?
It would be, you'd put it to a log.
Okay, so I got the log I'm going to use natural log, I just prefer it, equal, first of all I got to, what's the first step?
Oh, you got to divide by 5 first.
Yeah, you got to isolate all of that.
Yeah.
I can't do it if I leave that 5 over there. So it's the natural log of 1.3 divided by 5 equals the natural log of 1/2. Hey, I guess I can multiply that t times that to get to the t over 12 power. Now I can bring that down in front, put it there, and
divide by...
now I can solve for 12. I can solve for t. T is going to be equal to 12 times the natural log of 1.3 over 5 divided by the natural log of 1/2. That's a negative number, or the log of that's a negative number. That's a negative number. So I got a negative number divided by a negative number. I'm going to have a positive time answer. All right, we got 4 minutes. Is there a problem on this page that you'd like to do in that 4 minutes? Would you rather do 28 and set it up, or would you rather do one of these up here?
I guess we can do 28.
Okay. A certain strain of bacteria is doubling every 20 minutes. So how can I write that? This is the general.
Can I just write it in general terms?
No, you have to, in other words, we gotta substitute for y, for a, and for t in order to solve for r. And that's always going to be the first step.
Can't we just divide t by 20 though? Wouldn't that work?
No. No. Why 20?
Because that's how many times it's doubling.
Here's how you do it. If it doubles, then it does that, right? A becomes 2a, and I know how long it takes to double. T is 20. Takes 20 minutes to double. And then what always happens here is the a's cancel. And now you're left with an equation that only has one variable. With me?
Yeah.
Again, we're going to do it exactly the same way. We're going to take the 20th root and subtract 1. So we get r equals 2 to the 1/20th minus 1. That's what r is equal to. Now use that in your original equation so that y is equal to a. Well, 1 plus r is going to be just 2 to the 1/20th power to the t. Now you can answer the second part. In other words, you can't answer the question until you solve for r. Okay. Well, they want to know how long the bacteria will increase from 10 to 1500. Well, that's 1500. That's 10. That's 2 to the 1/20th power, and that's t. Now we have an equation with one variable only. We can solve for t, divide both sides by 10, take the log of both sides, and go from there.
Mm-hmm. All right.
Jake, you good to go?
Yeah.
Okay. I think you are too. I think you should do okay on this test tomorrow.
Thanks.
All right. Talk to you next time.
All right. Thank you.
Okay. Bye-bye.